Hi, and welcome to this concept bite about phase equilibria. This is a concept we have seen before for both entropy and enthalpy as separate concepts, but in this video we are going to look at how pressure and temperature affect the Gibbs free energy of the system and consequently which phase is favoured. We have already seen phase diagrams, and it should not be too much of a stretch to understand that the phase favoured at any given pressure and temperature is the phase with the lowest Gibbs free energy. However, it is useful to be able to understand and model how small changes of temperature and pressure will favour one phase or another at a phase boundary. I should note here that there is no clear phase transition from liquids or gases to form supercritical fluids, and so behaviour around this region is described by thermodynamics not covered in this course. Just as a note for terminology, the melting and boiling point of a substance are defined at 1 bar. For all other pressures, we would refer to these phase changes as melting and boiling temperatures. At a phase boundary, two or more phases are in equilibrium with each other, and the value of the Gibbs energy is the same for both processes. We can see that if the pressure is constant, then the molar Gibbs energy of a system depends upon temperature with a constant of proportionality of minus the molar entropy. Consequently, the molar entropy of solids is the lowest and has the shallowest negative gradient. The molar entropy of a gas is biggest and consequently has the highest negative gradient on the delta G T-plot. And the liquid has an intermediate value. This sketch plot shows at pressures above the triple point how at low temperature the molar Gibbs energy of the solid is lowest, and so this is the favoured phase. As we increase the temperature, we reach a point where the solid liquid lines cross, and where they do, they are in equilibrium and we have a phase change. Increasing the temperature still further, we see that the liquid phase being favoured, and then the point where the liquid gas lines cross, their values of molar Gibbs energy are the same and the two phases are again in equilibrium. Finally, at high temperatures, it is the gas phase with the lowest value of the molar Gibbs energy, and this is the favoured phase. If we instead look at temperatures below the triple point, we see that at no point is the liquid phase the phase with the lowest Gibbs free energy. Consequently, a liquid is never a stable phase below the triple point. We can also look at how the molar Gibbs energy changes with pressure for different phases, but we have to look at two different equations here to describe the Gibbs energy, because we know from the ideal gas law that the molar volume of a gas is dependent upon pressure. This isn't true for the solids or liquids, or at least the molar volume dependence is negligible. The larger the molar volume, the steeper the slope on this graph. So again, by modelling these equations, we can say that at low pressures, the gas has the lowest value of molar Gibbs energy, and as the pressure increases for the system, we favour the liquid, then the gas, as the molar volumes decrease. If we look at how small changes of pressure or temperature affect the transition between liquids and gases, the Clausius-Clapeyron equation may be derived. The equation is out with the scope of this course, but the result is relatively simple. It relates the pressure to the temperature by the enthalpy of vaporization of the system. It tells us that if at any pressure and temperature P1 and T1 we are in thermodynamic equilibrium on a phase boundary, then if the pressure is changed, then to maintain the equilibrium, the temperature of that transition must also change, or vice versa. We are likely already familiar with this, as liquids have a tendency to boil at lower temperatures as the pressure decreases. This is the reason that mountaineers, who took themselves up the big hill, moan that they can't get a good cup of tea after their endeavours. If we look at this graphically, we can see two lines for each of the two phases, the higher of each set at higher pressure than the other. The gradient of these lines against temperature for each phase is unchanged because this is the entropy of each phase, but the relative position of these lines changes as when the pressure increases, so does the Gibbs energy. The amount each line moves depend upon the molar volume of each phase. The point where these lines cross is the boiling temperature, and we can see this graphically move. We have already seen an example of these lines for phases moving up and down relative to each other when I showed you how the temperature and Gibbs free energy are related below the triple point. If instead we look at the solid-liquid phase boundary, then the change in pressure of the phase change and the change in temperature of the phase change are related by the enthalpy of fusion. The change in molar volume of the two phases and the temperature of the phase change. This relationship is called the Clapeyron equation, and it works because there are only negligible differences in the molar volumes of solids and liquids. Again, if we examine this process graphically, the molar entropy of the liquid is higher than that of the solid and so has a steeper gradient. The relative amount these lines move is of course related to the pressure, with larger change in the positions of these lines for phases with larger molar volumes. Water is unusual in that ice floats on water. This is because the molar volume of ice is higher than the molar volume of the liquid. Or, in terms of density, of which you're probably more familiar, the density of the solid is lower than the liquid. Consequently, the gradient of the solid-liquid line on the phase diagram is negative. This means that as pressure is applied, water melts at a lower temperature. We see this in action in the use of ice skates. The skates have a narrow blade to minimise the area over which the weight of the skater is applied, or to maximise the pressure which is applied. Consequently, the low friction seen by ice skaters is not due to skating over ice, but rather skating over a near frictionless thin film of liquid water. I hope that you now have a better understanding of why temperature and pressure are so intrinsically linked with the equilibrium phase of a system. We have seen how we can determine values of temperatures and pressures of phase changes by knowing their behaviour at one point, and we perhaps have a better understanding of just why water is so unusual. I look forward to seeing you in other videos, and as always, if you have any questions, please do not hesitate to ask.